Let's spend some time talking about ExpressRoute, one of the most popular Azure networking products. Continues to be that way even after nearly 10 years of being in service. And let's specifically talk about high availability, BCDR, failover, and making sure that our networking design, specifically our hybrid network design, is aligned with all of the other choices we're making in Azure in terms of compute, storage, overall use of the cloud, and our business appetite for risk. And let's talk about some common errors. So I've got about 11 patterns for you here, varying from issues with gateways, issues with circuits, issues with on-prem equipment. And I'm going to talk through a fairly network topology-centric view of these design errors. I'm not going to cover things like cost, monitoring, things like BFD, very specific sort of low-level details. This is very much a whirlwind tour, high level of the most common patterns that we see. And who knows, maybe you'll spot something that's of use for your network design, and maybe some of the features that I talk about might be useful to increase your availability and uptime of ExpressRoute, which, for most customers, especially large customers, we continue to see some sort of hybrid use of Azure. So whether you've got part of your application left on-prem or some sort of service that you rely on-prem, we have to remind ourselves that the bit that stitches on-prem to the cloud together, our hybrid connection, ExpressRoute, is just as important as the bits on either end. So we need to make sure, again, that the design decisions we're making are aligned to our wider cloud strategy. Okay, so let's start with possibly one of the most common scenarios that we see, which is, if we look at this diagram here, we've got our on-premise network on the left, and on the right-hand side, we've got a relatively common pattern. This customer here has decided to use Azure in multiple regions. For example, in Europe, it might be I've gone for West Europe plus North Europe, or maybe UK South plus UK West. And I'm probably doing that because I want some sort of regional availability. So if one region goes down, I've got some sort of capability to either use active services in the other region or spin up DR services. But at some point, we've communicated internally and made a decision that, yep, I want to mitigate the risk of an entire region going offline. And the design error that we see here is we're connecting our on-prem network into Azure just using a single ExpressRoute circuit. And this is one of the main communications in this video, is that whilst a single ExpressRoute circuit is highly available, of course, we've seen in previous videos, if you dive inside of a circuit, this circuit is deployed inside of a single edge location, a point of presence, like an Equinix facility or a telehouse facility. Inside of there, we'll have multiple Microsoft routers, and we can have a primary connection and a secondary connection. So inside of the facility, there's high availability with separate physical and logical paths. So if one Microsoft router goes down, you've still got reachability. Those routers, though, are going to be in the same geographical area, most often in the same building. And because of that, our network decision here is now out of sync with our decision for our consumption of Azure, because if that single geographical facility goes down, we can no longer reach into Azure. And whilst these facilities often have diverse power, cooling, separate Microsoft routers, many network paths, etc., we can think about events that would take out the entire facility. And even though these are rare events, if you work in IT for a long period of time, if you work inside the data center space especially, you'll know things can happen with air conditioning. I remember maybe over 10 years ago now in the UK, when the volcanoes were going off in Iceland, the dust clouds that were floating around. I remember being in London at the time. A lot of the data centers were really worried that the dust was going to affect the cooling in the facilities. And lots of data centers had like windows open and additional cooling, etc. So there are rare events, natural events that can cause complete facility outages. And it's for this reason that in this diagram here, to make this customer's ExpressRoute design aligned with their Azure design, we'd look for a second circuit in a separate point of presence. So, for example, again, taking a UK-centric view, if the customer's got an ExpressRoute circuit in the London 1 POP, Microsoft has another POP in London 2, which is another co-location facility, which is about 30 miles apart. So you've got that geographical resilience to align your POP resilience with your Azure resilience. Of course, those regions are many miles apart. And the green box here, I want to flag a new feature that we announced recently to help customers make this decision in a more informed way. So let me flip to the documentation for that, and we'll go through that. So this is the new experience we have for deploying ExpressRoute circuits. And you can try this out yourself. If you go to the marketplace and search for ExpressRoute Preview, you'll get a different experience now when you deploy a new circuit. And what you can actually do is, when you deploy your circuits, let's say you're deploying Azure for the first time, and you want to know, okay, which POP should I use? Which POP you use is very important because only certain providers in certain POPs. But for performance reasons, also if you choose POPs that are really far apart, for example in the US East Coast and West Coast, maybe you don't get the performance that you want. It's less of a factor when you've got metro designs where you can have, for example, London 1, London 2, Amsterdam 1, Amsterdam 2, where the geographical distance is a bit smaller. But the bit I want to flag here is this new experience. It was announced last month in preview. You can go into the Azure portal and it will tell you the actual distance between the peering locations for you to make a more informed decision. Okay, back to our presentation now. This one is kind of similar, but again, I think it's worth calling out because it's a similar theme here, which is on the right-hand side, this customer's chosen to use a single Azure region, but inside of that Azure region, they're using availability zones. And we know that availability zones are chunks of Azure in that region, separate data centers with completely separate power, cooling, fiber, etc., etc. So again, at the Azure region level, including the ExpressRoute gateway, which is, here we see ExpressRoute gateway, it's an AZ SKU, which means under the covers, the ExpressRoute gateway function is spread across multiple availability zones. The implicit design here is saying, look, we want to mitigate single data center failures, single geographical points of failure in our Azure region story. And we have the same problem as before, whereas the bit on the right is not in sync here with the bit in the middle, because the bit on the right is using availability zones. Now, we don't have the concept of availability zones for our points of presence. They are single facilities. So what we need to do to this design to bring it in sync is the same as before. We need to deploy another ExpressRoute circuit in another POP, and then we'll have geographical diversity in the POPs, geographical diversity using availability zones in the regions, and again, the portal experience is relevant here as well. Okay, now we have the reverse of this problem. This customer here has spent the time to connect to the Microsoft Edge with multiple circuits in multiple diverse POPs, and we are stitching that through to use of Azure in a single region with availability zones for our compute, our storage, our PaaS services. But the design error here is the ExpressRoute gateway is using an older ultra performance SKU. So this is still giving the 10 gigabit per second throughput, but these non-availability zone SKUs, they are deployed within availability sets inside of a single availability zone. Therefore, the diagram here is showing that this bit in the middle, the gateway layer, has a single geographical point of failure, and that's the bit that's out of sync here with our VNets and spokes and compute on the right, and our circuits in the middle. So for this customer, we would want to uplift that to the availability zone SKU, the ERGWAZ3. And the new feature that's relevant here that I want to talk about very briefly is the gateway migration feature. So this is another feature that's in preview, and this gives you the ability to do something in Azure which has not been possible before, which is to move from a non-AZ SKU to an AZ-enabled SKU without having to do a complete rip and replace of the gateway. So before this feature, you would have to delete the old gateway, It could take 15-20 minutes. And for that, as soon as you start doing that, you've got complete loss of connectivity to on-prem. And then you deploy the new gateway, which can take another 20-25 minutes, re-establish your connections, etc. Only then do you get connectivity back. So before you were looking at maintenance window, planning of maybe 2 hours downtime, this is a more seamless failover. This is going to be very interesting to mitigate this design error that I'm showing here. So if we take anything away from this video, definitely double click on your design, because a lot of customers have multiple circuits in Azure, but a lot of customers also have the non-AZ SKU gateways. So let's make sure we're sort of marrying up the resilience choices we're making at each layer. Okay, the next one. So this customer's got the multiple circuits. We've got availability zones everywhere, including the gateway in Azure. But back on premises here, this could be all the way back in the data center, this customer edge device, or it could be some sort of CPE device on the edge of an MPLS network managed by a customer or the incumbent WAN provider. But ultimately, we're stitching together the multiple connections to the Microsoft Edge into a single CPE device. So this will be a total of 2 BGP sessions on the top here, 2 BGP sessions on the bottom, and then some sort of network in the middle here, back to a single device with sub-interfaces and things like this. But obviously the single point of failure here is the customer edge device. We've gone to all this trouble on the Azure side and spent all of this money to get the right level of resilience, but we're coming through a single customer edge. So it doesn't marry up from left to right. Okay, this next one is something slightly different. This is we've got the right availability zones in the region, we've got the right gateway, we've got the right number of circuits, we've got the right number of CPE devices, but we've made a decision here, and I'm not specifically saying this is completely incorrect. We just need to make sure that we understand the behavior here, which is we've got a primary circuit which we're using under normal conditions through this top point of presence at 10 gigabits per second. And we've got a standby connection here that we're not using under normal conditions, where we've provisioned a circuit at 50 megabits per second. And the expectation here might be, well, if this top point of presence goes down, I'll just flip over to the backup circuit and I'll increase the bandwidth to 10 gig. And whilst that may be possible, we're making an assumption there that the capacity will be available. So it's worth double clicking and going into the ExpressRoute documents here to understand the behavior of ExpressRoute circuit upgrades, because depending on the available port capacity at the time of clicking upgrade, the circuit here may or may not support that seamless bandwidth upgrade. If it doesn't, then as the documents say, you have to delete the circuit and recreate, so you'll be taking an outage to do that anyway. So like I say, this is not specifically incorrect. It's just about making sure that what happens in a DR event is aligned with your requirements in a DR event. This next one is in a similar vein. So here we've got a coexistence scenario. So we've got ExpressRoute alongside VPN, which is fully supported. We've got many customers doing that. And this customer's decided, I've got a 10 gig circuit at the top via ExpressRoute, and then for my backup, rather than deploying a second ExpressRoute circuit, I'm going to go for a VPN backup. This is a perfectly acceptable design decision, and we've got, like I say, we've got many customers doing this, but I do want to call out some of the potential pitfalls here and things to watch out for. The first one would be, where are we terminating this VPN in our network? Because if our on-premises firewall here can only support maybe 1 gig of throughput, whether it's due to the device itself, the license, or maybe the internet breakout we've bought from the ISP is only at 1 gig. Obviously, we're not going to get 10 gig throughput on a 1 gig infrastructure there, which may or may not be suitable, right? Some customers would happily accept a lesser throughput in DR because it's a exceptional event. The next thing I'd call out is if you are trying to get up to 10 gigabits per second of a VPN, there are more complicated scenarios where you can you can get more VPN throughput. Generally, if you look in the Azure docs, depending on algorithm, each VPN tunnel tops out at between 1.25 and 2 gigabits per second. So you can use more complicated BGP, ECMP, multi-tunnel designs to get higher aggregate throughput. But again, you're starting to increase the level of complexity at that point. Maybe you're better off just deploying a second ExpressRoute circuit. The last thing I would call out on this page here is, in my experience, one of the complex areas here to watch out for is this ExpressRoute circuit. When it comes into your network, it's coming into probably an area where you terminate private connections. Many customers treat Azure as an extension of their data center because it's their private VNet. They manage that slice of the cloud for them, and this is a private circuit for them. Whereas a site-to-site VPN would probably be coming into their network into an internet edge firewall, which may or may not be normally used for connectivity to other private networks that are yours. The point here is you need to make sure that the sort of required stitching is done internally. Maybe it's a different team that manages the firewall. Does the firewall have all of the same rules as any sort of interim firewall that you may have here? Is the routing in place to allow this, etc., etc.? Okay, this is a similar scenario with asymmetry, but this time the asymmetry is being caused by BGP configuration. So this customer's kind of gone for a multi-ExpressRoute design, and the problem that we see here is on the top, let's say that's our primary connection, we've gone to the trouble, we're advertising all of our networks that exist on-prem. Let's pretend we've got 5 networks on-prem. We advertise via BGP all of those prefixes. And under normal conditions, Azure can see all of these prefixes, and we configure BGP traffic engineering to make sure the top path is used. Maybe we don't test the backup path, and when we find we need to use the backup path, we find that, for some reason there was a prefix list or some internal LAN, WAN redistribution, which meant that only one of the internal networks was being used. So the point here is we need to make sure that if we are using multiple circuits, the BGP configuration, at least from a filtering perspective, is symmetrical. And like it says here, the same applies to any firewalls that are used. We need to make sure the firewall security config is mirrored on the backup, and that goes down the rabbit hole of, are they separate firewalls, are they clustered firewalls, is it active-active, etc., etc. Okay, now we're diving into a single POP. I've made an entire video on this in the past. The link is there. I'll leave it in the description. But just to call it out again, so inside of a single POP, a common error is when you connect your routers to Microsoft. Generally, we recommend you run the 2 legs of a single circuit active-active, so you can benefit from ECMP and the bursting capability of ExpressRoute. But also because, as this video talks about that I'll link to, when we do maintenance on our routers, we prepend routes to you to sort of drain connections and tell your network, move on to a different path. If you're using BGP wait or BGP local pref, then they will sort of supersede the AS path we're sending you, and you can get yourself into a period of increased downtime, which you can mitigate by running ECMP. Okay, when we talk about ExpressRoute, we also have a feature called ExpressRoute Global Reach, and we use ExpressRoute Global Reach inside of Azure to reach solutions like Azure VMware Solutions and SkyTap on Azure. In this design here, the customer's sort of native use of Azure is all fully resilient to the right gateways and AZs and multiple circuits, and the customer's adopted AVS. But the design error here is, even though this is all functionally working, nothing is incorrect in terms of base functionality here. We've got reachability to AVS. The problem here is where that red warning sign is. There should be another global reach connection that connects the AVS circuit to this backup ExpressRoute circuit. Otherwise, if this POP goes down on the top, we've got reachability to native Azure VNets, but we lose connectivity to AVS. So just making sure that our global reach resilience is married up with our normal ExpressRoute and Azure resilience. Okay, let's talk about a different topic now, which is a circuit hairpinning. And this is one which a lot of customers are perhaps not aware of, and that is if you connect multiple gateways to the same circuit, then they will redistribute the routes, not only to on-prem, but to the other gateway. So in this diagram here, region B knows about region A via the circuit. And whilst that's technically functional, we strongly recommend you do not use that path for inter-region traffic. And there's a few reasons for that. Let me explain. So first one is, depending on where that POP is in relation to the regions, you can get really poor performance in terms of latency, because you're sending traffic from two regions that are close together via a POP that's really far away. So that's reason number one. Reason number two is this traffic comes into the region via a gateway. So your inter-region traffic is sharing the bandwidth on this ExpressRoute gateway, which should only really be used for on-prem traffic. So you can see there's a muddy in there of the water. What if you do a very large inter-region bandwidth transfer? It could impact your reachability to on-prem. So we never want to cross the wires in terms of cloud resilience and hybrid resilience. The next reason is on that point of resilience, which is, well, what if that point of presence goes down? If the point of presence goes down, you can understand you lose connectivity to on-prem, and go back to the slides we talked about earlier, have multiple POPs, etc. But if you weren't aware of this behavior, would you expect an ExpressRoute point of presence going down to affect your region-to-region traffic inside of Azure? Surely that traffic should be using the Microsoft backbone. Well, if you haven't engineered your network in the right way, that won't be happening. So the strong recommendation here is make sure we're using global VNet peering or virtual WAN hub-to-hub if you're a vWAN customer. And this is covered in this article here again, which I'll link to, about the sort of some of the downsides that I talked about. And there's also a link here to some of the features that are coming out in the next couple of months in Azure, where we will allow you to toggle the ability to filter out routes from other gateways via ExpressRoute. So watch out for more information on that in the future. Okay, and the last one. So thanks for sticking with this. Hopefully you found it interesting. But the last one here, again, this is even more nuanced than the esoteric knowledge, but the really interesting one to be aware of, and that is, let's think about a single region now. Let's look at the address space of these spokes, 10.100.10.20. Some customers, when they advertise in their routes into Azure, they don't advertise all the specific networks, they just advertise in a supernet, like a 10/8. What will happen in this diagram here is when spoke A talks to spoke B, if there's no other routes like UDRs, etc., to a firewall or an NVA in the hub, this traffic will actually be attracted via the best route winning down to the ExpressRoute circuit. And then the ExpressRoute circuit, because it knows about spoke B via the gateway, the traffic will actually go this way. So you can end up with this strange scenario where traffic between two spokes in the region is bouncing off the ExpressRoute circuit, which could be hundreds of miles away. So you can imagine there's lots of performance reasons and scalability and resilience reasons why you really don't want to be doing that. So if you notice very high latency on spoke-to-spoke traffic, this could be one of the reasons why. Thankfully, most customers have adopted a virtual WAN or are using the tried and tested hub-spoke method via Azure Firewall or an NVA with UDRs, etc. Anyway, I hope you found that interesting, that whirlwind tour of ExpressRoute resilience. Maybe I missed out a scenario. If you've got anything in mind, any ideas, drop them in the comments below, and I shall catch you in the next video. Thank you.